Hello friends and welcome. And welcome, by the way, to this first installment of a mini-series on power supplies. And where this starts was a couple of months ago when I finished that speaker there. And I knew it had all the qualities that I wanted out of the speaker, and it sort of immediately was clear to me that I should then start working on the rest of my chain and leave this a bit alone, improve it, but not build a new speaker, just optimize this further. And the next item on the list is probably the most, I would say, is the most important aspect, and that is the power amplifier. And the challenge I set myself that a couple of months ago was that my strategy would be the following. I would take the best exemplars of what I had done prior, which was a 26 4P1L amp, which is a differential amp. And I would take my best single-ended amp, which is a 26 driving a 40, type 46 driving a type 50. And I would use those and really optimize, and in my approach everything would be suspect, because what I had noticed that once you got decent materials, you got decent output tubes, you got everything at a good level, there is no magical ingredient anymore. There is not a magic capacitor, there's not a magic output tube, there's no such thing. It is all about your concept, the topologies that you choose, and then having everything fit those topologies. And whichever way you approach that. And so you have topologies on the amplification side, and you also have very distinct topologies on the power supply side. And with my first project, which was that, which I have reported on, that was the 8532W driving a differential pair of 4P1Ls. And one of the things I found there, for example, is that I had a critical inductance filter, because one of the things up until that amp, I had always used a LC power supply, so a double pi filter. But what I noticed, and I was suspect that it was the circuitry, was that it tended to motorboat, so the power draw would go up and down, and also the sound quality wasn't consistent. You had whole patches where this amp just didn't sound good, and then it sounded good, and you had these sort of golden moments or golden electricity moments. And I personally think now that it was down to the power supply, because this amp and the last amp didn't have exhibited that behavior at all. After they warmed up, they would sound great. And with that last amp, so with the differential pair of 4P1Ls, I actually, for example, put after the LC stage. So that's, by the way, one of the topologies that we're going to have a look in this video. We're going to have a look at 3 topologies. So I noticed, for example, that if I then had an extra inductor feeding the output transformer and then the 2 tubes, that had a dramatic positive impact on the sound if you chose the right value and the right core material. So I ended up, for example, with a choke that was 7 Henrys, rated at half an amp, and only 22 ohms, and it was an amorphous core, and that just sounded optimal for that type of amp. So that gave me a strong indication that power supplies made, and the topology that you use can have a strong influence on the sound. And but that type of power supply, for reasons that we will get into, is not so suitable for a single-ended amp. I personally at this point think that you shouldn't be using a critical inductance filter for that. And again, by the end of this series you know exactly why, and you will have seen it under dynamic conditions why. So with this amp I went with a different topology, and which I'm still sort of fine-tuning, but it has given rise to a couple of things. It's very tunable, which is nice, because you get to sort of dial in the level of the speed and smear, and so you get to dial it in very nicely. which is unique to this topology. And it performs really well. It has excellent regulation, excellent recovery characteristics, low hum, so very good. I really like it. So now, in my last video, I described that type of circuitry in my test setup, because I always share on which conditions I do the test. And of course, one of my very attentive and long-term subscriber and supporter of the channel, Hugo Bloemers, had noticed it. And I'll read out his question in a second. But I thought the best answer, I'm going to answer his question in this video, but I thought the best thing also is to actually do a complete overview of the three main topologies. So the topology that I use, the critical inductance led, so where you have a choke first, a large choke of critical inductance, a smaller choke, and some of the facets that come around with that. And then the traditional power supply filter that I would use, which is that CLCLC type of filter, which has a tunable cap. So we're going to look at everything, we're going to compare it, we're going to look at all the characteristics, and then in one of the next video we're going to also dive into Duncan's PSU Designer software, and I'm going to show you, unlike most people who show you how to sort of look at the voltage and minimize hum, we're going to look at a whole lot more. So we're going to look at diode switching noises, which are indicated by the angle of the conduction cycle, how that comes in. We're going to also look at the recovery characteristics. We're going to look at output impedance. And all of those things we can mostly do in Duncan's PSU Designer software. There's only a couple of things that you have to do in, for example, LT-Spice or P-Spice or a simulator like that. We won't do that in these videos, but we're gonna do a full deep dive in how to optimize your power supply in Duncan's PSU Designer software. So that's all to come. I hope that will be interesting, and this is very much a total guide, and I thought that would be the best way of fully answering Hugo, but at the same time serve everybody with some better understanding of what you can optimize and give you more, more tools in your toolkit, really. So that's to come. Let's move to my computer where I've prepared some sheets to sort of get this all started. See you there. So here we are with Hugo's question. And Hugo writes, "Hi Edward." And he does this in response on my last video where I reported on trying 7 rectifiers in a specific setup. So he said, "Hi Edward, this has been a great series of experiments you did. I've been going over the setup of the tubes and I noticed you use the following topology." And by the way, I laid out the 3 big topologies that Hugo is now referencing and with which we're going to discuss in detail. So he said, "I noticed you use this small inductor, small cap, large inductor, large cap. I always thought," he continues, "that the following topology was universal. Large inductor of critical inductance, small or medium cap, and then a small inductor and a large cap. Could you comment on this, please? And do you have experiences with both or any particular reason to follow your topology?" Well, of course I do. And already in the introduction I told you that the third topology that I used to use, to me, had suspect sound quality, and it also has specific negativities that we're going to look at in a second. I'll put it in an overview. So I now move to a topology that looks a lot like this. And I find this to have superior characteristics, to be short. But in my last amp, which was a push-pull amp, which has different requirements, and we're going to talk about this as well, I use this type of setup. So yes, I do have experience with both, and both have their own purposes and pros and cons, really. Next one, he continues, "Janos likes to put in a small capacitor, let's say small than 4 microfarad. And by the way, that is because that is the stated limit on the datasheet for the 5R4GY. So then you get a circuit like this, a small tuning cap here. And he said what I like about this model is that you can fine-tune the B+, and it gives some extra smoothing. What are your thoughts on this practice? And that's correct, because what you basically have here is a 3-stage filter. So you got an LC, LC, and you got a C stage. So of course, in terms of hum reduction, this will be better unless you add an extra stage, which is definitely an option. Now, this is often used as a tuning cap, but in this circuit that I am currently using, you can actually tune both of these. So this one has an optimum value, both sides of which the voltage goes down. So it has sort of a peak. So you can actually scale it in 2 directions and modify the voltage. And same with this one. So generally, if you're coming from a high value, the smaller you make this, the higher the output, the higher the output voltage is. But you can play around with the inductor and the capacitor value to combination. It's the combination that tunes it, and it also determines, if you look at the recovery characteristics, if your amp starts drawing a little bit or a little bit less current, is how steep the correction curve is and how much it overshoots or not overshoots. So you have basically 2 things that you can tune here. So you get the same options, you have the same tunability, but there's other characteristics. Now let's get into an overview of these 3 types of power supplies. So this is what I prepared. And I hope you can see this nice and clear. So we've got 3 power supplies. We always have them in this order in this video. So we've got the critical inductance, so the choke lead with critical inductance. And then we got the small choke lead. And here we got Millie. She likes to join our lesson here. Hey, and then we got the, if you will, the classical supply. So all of these 3 supplies go here, Millie. All of these I've of course used and have experience with. Now in general, all of them are of course tunable, but in general what you'll find is this. So the critical inductance thing, type of supply, and we're going to use in Duncan's PSU Designer and also in my next slide, so you can see some, I'll show you graphs of how this actually works. So the critical inductance has very good voltage. The voltage that you get out of your circuit is relatively low compared to your transformer. It's also not tunable. Ripple can be decent. It's actually really comparable, but because I had a 2-stage, it is not that good. If you add an extra stage, of course, or you use higher values, you can always reduce this. This is sort of the easiest to modulate. Noise reduction is extremely good because this type of topology exhibits the most a near continuous conduction cycle of the diode. It is nearly always conducting, and that means that the switching noises and the peak current is the lowest of any of these circuits, and that means you will naturally create the lowest rectifying noises. So lowest current means lowest noises from the circuitry, lowest crashing of current into the capacitors, all of those things. So regulation is extremely good. However, there is a trade-off going on with the recovery characteristics. And the recovery characteristics, what we talk about is once your amp asks a bit more current, or for example your mains goes up or down, your amp will settle at a new level for the moment. And the way that recovery to that new level goes can either be fast or slow. And it also can have ringing, it can have overshoot and just ring for several seconds even if the components are chosen wrong. So you either, in the recovery, you either have ringing, so you have a correction that takes a long time to settle, or you give up the nice regulation, so your output impedance goes up. That is a trade-off that type of circuitry has. Then let's go to the classic circuit. Voltage is of course tunable. You get a relatively high voltage are you able to get out of your transformer. So that can be up to say 1.3 times higher than the voltage that you have on your transformer. Ripple reduction is very good, and that's purely by really being a 3-stage filter and not a 2-stage as the other two there. Noise is the worst of all of them because the conduction cycle is really short. The current crashes into this capacitor, which is fully open, so you have a very low, the peak is very high, the current is the highest, the inrush current is the highest of all of these, and also the angle with which that current starts coming in is the highest of all of these circuits. So that is poor. So you better need these other stages to filter out that type of effect, and I still think it's very audible. And I think that's also the reason why people used oil caps here, so that they're a bit slower, actually have a lot of internal resistance and inductance to slow that down. But that's speculation. Regulation is not very good. You have a very high output impedance, as we'll see later. And recovery is quite slow, but it's smooth. So this amp settles very slowly. So when there's a change in demand, you'll see that it will go very slowly. It might take half a second, maybe even a second to actually get to its new level. So it's not, it is slow to set. It will settle very smoothly, but it's slow. Then the in-between circuit, which is really not an in-between circuit in a way, it's its own thing. Again, the voltage that you can get out is very high. It can be even higher than that, even with small capacitor values. That's because it's sometimes termed a flywheel effect that you can generate here, which is a highly efficient way of dealing with the incoming energy. Ripple reduction, being 2-stage, is sort of in the middle. Noise reduction is also in between these two. There is a inductor sort of making sure that this capacitor is not directly coupled to your diodes, so that gives smoother charging. But it is of course not near as smooth as that one. Regulation is extremely good. Just can be is very equal to the chocolate. If you configure it right, it's a bit configurable, and the recovery is as fast as this, but without the ringing. And it's also tunable. So what I found in my amp, and I've been playing around with that I can sort of, when I have a very reactive amp, it gets a bit more, if you will, drier and more detailed and very crisp in a way. And then if I slow the recovery a bit down towards this circuit, but not as bad, you get a little bit more smear and the amp becomes a bit more fuller sounding, but some of the details disappear, I found. So, but it is a very nice tuning aspect that you can optimize the type of sound to just fit what you're trying to accomplish. So that's my short overview of, perhaps also for you, Hugo, the reasons of using any of these circuits. They all have their pros and cons. To be honest, so since we're here, I can really say that at the moment this would be my go-to. And that might be a go-to, I don't know yet, for a push-pull amp. Last amp I used this circuitry. This amp uses this one. I think this one is more suited for a push-pull style amp that are in class A. Else I would grab for this circuit. Even if it is needed, and you want it quieter, what I have done is work with smaller inductors and make it a 3-stage. It retains all of its characteristics, but basically what I get now is I get having 3 LC stages. Really, I'm actually getting I even exceed the performance of this type of circuit in hum reduction. So that's the overview. That's the short way of answering you. We're later gonna really dive into the whys, but before we do that, I want to share one more thing, and that is, I think we just need to be clear on what a power supply filter needs to do and how it fits in. So before I get into these 5 rules, or 5 requirements that a power supply really needs to do, and why I'm also mentioning this is because this also gives us a little bit, this is related to the criteria that I just listed, you know, all the different characteristics. They come out of the requirements really. And if you, let's keep this model in mind. So we got our transformer, we got our rectifier, then we got our power filter, which we're starting out, that can have one of these 3 topologies. And there's also variants on these topologies, of course. We won't discuss in this video, in either of these videos, regulated supply, whether we pass or shunt. We won't talk about it, but anyway. And here we got our output, the output tube, and we might have an extra filter, and then our input tube or driver tube. So that's the structure. So let's look at the requirements for a power supply that I think a power supply needs to do. First, and these are pretty straightforward, don't worry. Provide a load on the rectifier so that the rectifier switches on and the current flows in one direction into the filter. So what we want is this needs to provide a load on the rectifier so the current starts moving in that direction and in that direction only. Simple, eh? 2, very important, store up energy and deliver it to the load even if the rectifier is not conducting. We have our load, we don't want the music to stop if there's no power coming out of the transformer. So we'll need to store up energy and deliver it to the load even if we don't get anything in. Makes sense, eh? Number 3, provide a low source impedance to the active circuitries at frequencies from DC to the ultrasonic. So whatever our output tube or our driver tubes are demanding, we want the filter to provide a low impedance, which means it doesn't matter what the load is doing, what the signal is. And of course the load is different for single-ended and push-pull. The demands are different. We'll talk about that as well. But what we want is a low output impedance, which means that the B plus doesn't sag and it's as constant as possible, which is accomplished by having a low source impedance. Number 4, now and this is the focus of a lot of people, is reject hum and lesser and noise and keep it from getting to the power output supplies. And I want to qualify something with this. So we have this, we get the hum because we have a 100 Hertz or 120 Hertz pulsating thing after the rectifier. Plus we get some switching noises from the rectifier here. So we got hum and noise getting into the filter here. However, there's something more. With a single-ended amp, it produces something specific because the sine wave of the music, and that is a complex sine wave, of course, that impresses all kinds of frequencies that will travel this side into the filter. So when we say we want to suppress, reject hum and noise and keep it from the output, we also want to prevent it to getting to the other one. For example, with a push-pull amp, and I'll get into it in a second as well. With a push-pull amp, we actually what is being loaded up is because the 2 tubes are in counterphase, is that the difference between the 2 tubes creates a certain kind of noise because those 2 tubes are never the same. The distance between the load lines is not the same. So you get a very weird signal being impressed, which is not music, it's a distortion signal, and it travels into your circuitry. So we want to also, one of the functions of your power filter here is to prevent that noise from getting to the other tubes. Now when it's a single-ended amp, of course what happens is this is the music signal. So if that gets to the input tube or your driver tube, it basically has positive or negative feedback. So that's a bit the effect that it can happen depending on the phase of the coupling and so on. It'll actually have a relatively moderate impact that we can actually use. So then it's not really hum or noise as you get with a push-pull amp, where you probably want to isolate your driver a bit more. But with a single-ended amp, it's a lot less harmful. And then number 5 rule that we want out of a power supply filter is do this on all circumstances with good recovery characteristics. And what we're saying here is basically, if things change, we still want all these functions to keep operating very nicely. So it needs to have it needs to be stable, it needs to recover smooth, and it needs to recover fast. In the terms of that so that under all circumstances it produces a good sound quality. So let's talk about this a little bit more, just to summarize this. With single-ended, the load, you know what that we talked about here. The load there in the power supply, the load is the music signal itself. So the distortion on the driver is the music in phase or in opposite phase. With push-pull, the load is the non-linearity between the output tubes. If these tubes were entirely equal, of course you would have a constant current draw and it would have no effect. But that doesn't happen. And this, as I said before, this requires the driver to be shielded from the distortion generated by load. Now let's have a quick look at this facet. If you look at the power supply here, you see that for a single-ended amp, I haven't really painted in the circuitry for, but I might just have an RC stage to go to the driver. And as with a push-pull amp, so what I mentioned in my last amp, I had this type of supply. So I had a critical inductance supply, LC, and then I had an extra choke here and a voltage dropper and its own capacitor to decouple the driver stage from the output tubes. And this was my extra magic ingredient that made a huge difference, is putting this choke here. So it probably further decouples it, but it also creates sort of a constant current source for the output tubes. And that had a really nice impact. So, and this is highly specific. I would not do this for a single-ended amp, but this setup I felt was needed for a push-pull amp. So I just want to share this a little bit so that your thinking is not necessarily this topology versus that topology. You have to realize what your load is and what you're trying to what your circuitry needs to do, and then you start making the right steps, and then we can go in the simulation. Now, to finish this video off, we're going to look at one final thing. And by the way, in the second video, so the one after this, we're going to dive into PSU Designer and into the software, and we're going to dynamically play around with all of this, so that way you get hopefully you'll develop a real nice feel for these different type of power supplies. So I again made an overview, and this time we're going to look at these four elements. We're going to look at the ripple again, but we're now going to look at it in graph form. We're going to look at the conduction cycle, which is here in green. The ripple is the red one, and here's the scale. And we're going to use at the recovery. So if we have a different change in current demand, which can happen if you have a load line of a tube, you'll have different current demands on the tube. And if you have a very low base frequency node, say a 30 Hertz node, of course that lasts longer than the individual cycles that we get from the mains. So we actually, with those low base nodes, you can actually get more current demand and less current demand. Even if that means that you have more recharging to do. So in that case, we get a response from the power supply. And it can either be fast, or it can be slow, or it can have an overshoot like you see here. And in the next video, we're going to look at how to deal with it and to brush that out. And we'll see the trade-offs. So we have, again, our similar circuitries. So here we've got our critical inductance. Here is the power supply that I use. And here you have the typical caplet with a tuning cap type of supply. So if you look here, conduction cycle in green is the longest with a critical inductance. It's nearly conducting all of the time, only when the diode the voltage isn't past the forward voltage of the diode. Then you don't have any conduction, and then it comes up. And as you see, it just grows really steadily. And then if you look at the maximum here, it's about 130, nearly 140 milliamps that it maximum really reach. Now with the caplet supply, with the cap being directly connected to the diodes, of course, we get a huge inrush. So if you look at the uptake, you see that the conduction cycle is very steep. It reaches a very high maximum, so a bit higher than probably at 370 milliamps. So it goes up really, and then it slows down as soon as it has charged up that small leading capacitor. Hum is very low, 8 millivolts, so being a 3-stage filter, and these 2-stage filters only have about 75 or 80 millivolts. You can tune that with the values as well, but you can see with the 3-stage will naturally do better. So as Hugo said, it has extra smoothing. However, the conduction cycle is very wild, it's very harsh, it's very hard, it crashes in, and it lasts very short. My circuitry, whether we just add a small, we choose an optimal combination of these two, you can see that the conduction cycle is longer, and also that the uptake here is rather smooth. So the noises, the switching noises that you get from the diode will be less, and the conduction cycle, so it's all a bit smoothed out. And if you choose these really well, you can actually even get more efficient loading than having a cap there. So you can get a very high voltage out of relatively modest voltage on your transformer. Recovery characteristic is the final thing. This is the big disadvantage of this type of circuit, is that it has a very slow recovery. It takes about a second for it to fully recover. You can see this here. Even though I've helped it in all kinds of ways. So I've used 10 ohm 4 Henry chokes there, and these are very low inductance, low series capacitance capacitors. The only thing that is a bit sluggish is the input tube, but that's what I used to use, and what you also see, for example, Janus from Real World Audio use this tube. So when you do that, you're actually paying the price with a very slow recovery. This circuit, instead, having this type of setup at the start with a small inductor, has very fast recovery, and with the combination of these two, we can actually really not only determine the voltage that we get, but we can also determine the angle of it, and we can actually even go to this type of level. Voltage drop regulation, poorest over here, 11 volt drop by a change of 60 milliamps only. Here it has reduced to 7 volts. And here with the critical inductance setup, it's actually 6 volt, and you see that it is a very fast recovery. However, you can see the ringing. So in this setup, with this tube, we in this transformer with that impedance, we get ringing, and this actually also takes about maybe 600-800 milliseconds to stabilize. Now you can fix this completely, and you'll get a curve that is much similar than it, a little bit slower, if you add 100 ohms more impedance here. So if you do a type 80 rectifier, or you have a older style transformer with less, with a higher impedance, or you put just a 100 ohm resistor in there, you will actually, this will become smooth, still much faster than this in recovery, but not quite as fast as this type of circuitry, and we can get rid of the ringing. So with critical inductance, ringing is your issue. If you had a solid state rectifier in here, so very low impedance, this would look shocking. I'll show you in the next video, but it would look that, and it would take like about 1.5 seconds to stay, or even seconds to stabilize. I don't think that's a good idea. So tube rectifier with critical inductance works, but also with very low impedance, like I have here with the type 83 rectifier that I used to model this, or solid state, this will give you very nice characteristics. So that's the graph representation of the comparisons between these circuits. As said, in my next video we're going to play around in Duncan's PSU Designer software. And then we'll get to play around with this stuff, and I'll show you how to optimize the different aspects in PSU Designer. So I'll leave you with this slide, and that's what we're going to do in the next video. Thank you for your attention. I hope this was interesting. Go to buy me a coffee if you want to support this channel and more of these videos. Thank you for all the people that supported me already. Thank you to Hugo for supporting the channel and asking these questions and giving a nice lead in for the next series of videos. Thank you everyone for watching. I hope to catch you in the next video. Take care for now, and I'll hope to see you soon. Bye bye now.